Hello, everyone, and welcome to the Barclays Experience. We are excited to walk you through our sustainable and innovative dome design. Special thank yous to all the engineers, contractors, and architects shown here for making this project a reality. Here's our organization chart highlighting everyone's extensive work and roles. The Barclays Experience introduces a redefined interactive kiosk designed to captivate guests and pull them into the atmosphere of any event. As we begin the global assembly, you'll see the structural frame of the dome come together first. Once the frame is complete, the panels are placed one by one, each engineered for quick installation. Above the interior space is a slim layer separating the HVAC system, keeping it hidden while ensuring safe airflow. As the assembly finishes, our full LED facade activates across the dome surface. The animation cycles through the bold Roy G. Biv colors, demonstrating the clarity and brightness the panels can achieve. These LEDs are designed to work together to create full surface images, transforming the dome into a living display. Whether it's showcasing a concert theme, a football matchup, or playful cartoon scenes like Tom and Jerry or Snoopy, the system adapts to any event. It can even recreate your favorite moments like a chess match, The Lion King, your favorite structure, New York City at night, the winter season, or Kobe's iconic fadeaway shot. Here is our early cost estimation proposal meant as a draft to provide our contracting agency with a reasonable lump sum. Here's a more diversified portfolio of all arranged labor costs. One of the most important tools that guided our project was our Gantt chart. It kept our entire 12-week design schedule on track from our very first board meeting, helping our team to make this vision a reality. Speaking of reality, here's a finalized rendering of the experience we offer. Beginning with our power generator, then our LED control box, and finally our breaker to finish off our electrical subassembly. Then, beginning with our entry recognition subassembly, we have our dual wall camera setup for facial recognition, our iPad for user permission, and that will close off our entry recognition subassembly, also known as URSA. Taking a closer look at our local connections, each node or hub is connected using hollow aluminum struts, secured with standard bolts, nuts, and washers. The custom hub design recommended by our very own wind engineer, Shalom, also incorporates small shear walls that help control lateral motion and reinforce each connection. Here's an animation of our general intended assembly following the steps as shown here. Users will first position the base ring hubs and attach the struts in a ring-like fashion, building towards the dome's apex. Now here's our assistant project manager, Lucy.
Thank you very much, Steve. I'm going to talk about our work breakdown structure, and our tasks are broken down to three levels. Our first level is the geodesic dome. Then our second level has four sections. The first being design and assembly, is all the technical disciplines involved in the project, from structural to mechanical to electrical, lighting, civil, and modeling. And for our construction, we have the phasing, the slopes and risk analysis, the cost estimations, and the drawings. Then our analysis, we have the vertical and lateral loads. Then our FEA analysis and the foundation. Finally, for our project management, we have the planning and the scheduling. Our site is located in Piscataway, New Jersey, outside the SHI Stadium, which is home to the Rutgers football team. This location is very convenient because right in front of the stadium is where people naturally congregate before big events. So this will give our dome very high visibility as we intend to use it for ticketing and alumni information collection. And for our foundation, as this is a temporary structure, we decided to go for a temporary foundation as well because we do not want to interfere with any underground utilities. So we selected 10-inch textile plates, which will have 12 anchor points, and the plates being wide, it will give our structure enough protection against lateral loads. Then the flow and occupancy. This dome being a temporary occupant structure, we determined our maximum occupancy load to be 10 persons because we only have one clearly identified exit. So this will give enough egress, simplified fire protection and ventilation requirements according to the New Jersey laws. I'm going to hand over to Raj, who will talk about our architectural plans.
Thank you, Lucy. Starting with our architectural vision for the exteriors, our exterior design uses a continuous LED mesh facade over a honeycomb panel system, allowing the entire dome to function as a 360-degree digital display. The lightweight LED system is mounted using the bracket that do not overstress the geodesic frame and with the power routed through water conduits along the HSS members, so it is super safe. Now, why this matters? This matters because it creates an instant recognition, serves as a marketing magnet visible from the river road, generates the revenue through the sponsored content, and turns the dome into a digital billboard to know what's happening inside and what other events gonna happen in the future. Moving into our architectural vision for the interior. From a chaotic outside world, the atmosphere shifts to a calm, aurora inspired interior with a large open central space, clear walking paths, and wayfinding lights guiding the guests towards the ticketing. Ceiling level RGB lights creates a glowing aurora bands while acoustic treatments improve comfort. Again, the question why it matters. This interior reduces crowd anxiety, enhances clear visibility for the lines, provides a neutral backdrop for events, and allows visitors to visually reset from the bright and catchy exterior media to a calm interior, showing that this dome can give you a two extreme experience indeed. Supporting this experience is our mechanical system, which uses a central suspended ring ducts for even air distribution with low level supply and high level returns for efficient heat removal and ventilation. So, this system is scalable, efficient, and ideal for temporary event structures. Now, I'll be handing over the slide to Teja.
Thanks Raj, this is Tej. On this slide I am explaining how we analyze all vertical loads acting on a dome. This includes self-weight and the rain and the snow. We model the dome as a triangular 3D space truss, which means member mainly carries the axial compression or the tension, not the bending, because the dome spiritual geometry and vertical loads get distributed very efficiently down the ribs into the base ring. The curvature spreads the load across the 50 meridional ribs, so the force per member stays very small. This is why Doom performs extremely well under the gravity, rain, and the snow loads. In this slide, we are going to discuss the load calculation. Before running the FEA, we calculate the odd force by hand to establish a baseline. We assume the 5V hemispherical truss, pin connection, and the vertical load applied over the plane area. Using the spherical membrane theory, we compute the axial forces ring by ring based on the polar angle. The results shown even under the combined load, like self-weight and the rain, 5 psf and 25 psf of snow, each member only experienced the 140 to 460 pounds of axial compression. These values are extremely small compared to the strength capacity of aluminum membrane, and which already shown in the dome would be structurally very efficient. This is the final results of FEA vertical loads. Our FEA results match the hand calculation almost perfectly, and simulation confirms that member carries primarily axial forces and magnitude were consistent within the 140 to 460 pounds range as we predicted. The FEA shows no high stress area as we shown in the figure highlighted, and both gable frame and the connection hub remains well within the elastic range. Even under a critical plane drifting scenario where the crown member takes 2.6 clips of tension, the structure still is far beyond its material limits. Overall, the dome shows excellent strength, stiffness, and durability under the all vertical load conditions. From now, my friend Shalom will continue on lateral load analysis.
Thank you, Tessa, for discussing the vertical loads. My name is Shalom, and I'll be highlighting the lateral loads analysis in the project marketing. So the lateral loads include wind pressure or seismic or earthquake forces. We deem that the seismic loads are going to be neglected just because we have a smaller mass, which means lower inertial forces. So thank Newton's second law. Since we have a smaller structure, there's going to be a higher K constant, also known as stiffness, relative to the size, which also means there's going to be a higher natural frequency. If we have a higher natural frequency, we're going to be avoiding resonance, and it's essentially like the amplification of displacements or responses. Since we have a smaller sphere, there's going to be a lower center of gravity, which is going to reduce the overturning moment. So how does the dome resist lateral forces? We chose lightweight and stiff material, which is going to reduce the mass and seismic forces. And we know that the load path is going to cause the lateral loads to be transferred, as you see in figure 27. To validate the design, we initially performed calculations using the average East Coast wind speeds across all seasons, prioritizing the winter conditions to ensure maximum wind resistance. So we prioritize safety, hence taking a conservative approach to account for any unknown or unforeseen effects. These preliminary calculations were conducted using an online calculator tool as part of our prototype development. So the corresponding results are shown alongside to the right of the table. And these results were used to define the design envelope for the subsequent SolidWorks simulation study on the next slide. Finally, the previous load calculations were validated through finite element analysis, also known as FEA, and SolidWorks, which highlighted high stress areas mitigation. The following is a resulting image and video from the results in SolidWorks. So as you can see, the most susceptible area is the uppermost part of the dome, and it produces the most bending moment and axial deformation. However, our analysis concluded that the dome is structurally sound under wind loads and it's not required consideration of seismic forces conceptually. Now I'm going to be discussing our marketing plan. So on the slide includes our intended customers, the best way to reach our audience, and one of the media outlets we're going to be using is a flyer. So to the right is one of our example flyers. So it's a simple design, easy slogan, representative of our company identity, and vibrant colors, which is example why it's a good flyer. This is the first digital advertisement. I'll play it. So the strengths of this marketing flyer: it shows the conceptual design, it clearly shows the intended purpose, it depicts the intended location of the sphere, the audience can visualize being there easily, it's short and concise, and areas of improvement include adding the company branding or adding text or the company slogan. Now this is our second digital advertisement. I'll play it. I'm going to stop it for time purposes. So some of the strengths include that the editing style is marketed for younger audiences. It's hyper realistic, so the audience feels like they're there. There's hype music, there's no lyrics, so it's less distracting. Some of the improvements could be adding LEDs displays to showing a particular sports graphic in this advertisement, or adding text and company branding. Now Ruja will be discussing the SWOT and risk analysis, as well as the construction phasing.
Thank you so much, Shalom, for your calculation as well as marketing strategies. Now we begin with construction work. So we'll start with SWOT analysis. SWOT basically means what are the strengths, weaknesses, opportunities, and threats associated. Those strengths are sustainable honeycomb panel design, energy efficient dome architecture. Weaknesses associated are weather dependent assembly as well as specialized labor is required. Opportunities are partnership with universities, etc. And the threats include extreme weather conditions and market price fluctuations. Now let's move on with risk analysis. As we can see the assessment matrix which shows how negligible to severe the risks are involved. So structure assembly hazards, equipment failures, weather delays, etc. are the risk associated. And the highest risk which is associated is dome frame lifting and node connections work at a height. Mitigation include proper staged lifting plans, weather monitoring, skilled crew supervision, and secured bracing during assembly. Final stage of the presentation is here. It is the construction phasing. It consists of 14 to 16 weeks to construct a dome, and the equipment which are required are excavator, cranes, lifts, welders, etc. And they are done in many stages like site preparation, testing, electrical and interior, foundation, structure assembly, etc. Hope you liked our presentation. Thank you so much for your time and consideration.
Thank you, and please feel free to share any questions you have. Once again, thank you all for joining us, and we hope you've enjoyed the Barclays experience.